3 sprints. Gone. Not because the AI wrote bad code, at least not obviously bad. The team lead told me the PRs looked clean. Tests passed. Linting passed. The junior devs were shipping faster than ever, and everyone was celebrating velocity. Then, 6 weeks later, the on-call engineer got paged at 2 a.m., then again at 4 a.m., then every night for 2 weeks straight. What they found was a cascade of subtle failures. Race conditions in async handlers, business logic silently bypassed by over-permissive null checks, and database queries that worked fine under 10 users but choked at 1,000. Every single one of those bugs traced back to AI-generated code that was merged without a meaningful quality gate. The team sprint 8, and most of sprint 9 in pure firefighting mode. No features ship. Morale cratered. The CTO started asking hard questions. Here is the thing, none of this was inevitable. The AI did not fail them. The process failed them, and by the end of this lecture, you will have the exact process to make sure this never happens to your team. Now, you might think the answer is to just review AI code more carefully. But here is the statistic that should stop you cold. Adi Osmani, engineering director at Google, author of Learning Patterns, published a finding that senior engineers at teams actively using AI coding tools are spending 60% of their time fixing and cleaning up AI-generated code. 66%. That is not a productivity win. That is a productivity trap wearing a productivity mask. And the brutal irony. The junior developers feel fast. The dashboards show green. Commit frequency is up. But your most expensive, most experienced engineers, the ones who understand the system at depth, are being turned into cleanup crews. The root cause is not that AI writes bad code. The root cause is that there is no quality gate between AI generated this, and this is now in main. Without that gate, every piece of ambiguous, context-unaware, subtly AI output becomes your senior engineer's emergency. But what if we moved that quality gate upstream? That is the exact reframe this entire lecture is built on, and the specific mechanics start right now. So let me be completely direct about what you're going to walk away with after watching this full lecture. First, a 3-layer quality gate design, automated stalysis at layer 1, AI-specific semantic checks at layer 2, and a human review protocol calibrated to your team size at layer 3. You will know exactly what belongs in each layer and why. Second, a 25-item AI review checklist, grouped by failure category, correctness, security, performance, maintainability, and context awareness. Not a generic code review checklist. One built specifically for the failure modes that AI coding tools produce. Third, a minimum viable review process that scales. Whether you are a team of 3 or 30, you will have a concrete starting configuration you can deploy this week, not a 6-month process overhaul. These are not theoretical frameworks. Every item on that checklist and every layer in that gate design comes from actual postmortem data, actual production incidents, and 25 years of watching teams get this wrong in the same repeatable ways. The patterns are real. The tools exist. You just need architecture to connect them. Here is the central tension of everything we are going to cover. Take 2 engineering teams. Same headcount. Same AI coding tools. Copilot, Cursor, Claude, take your pick. Same deadline pressure. 6 months later, Team A has cut their feature delivery time by 40%, their production incident rate is down, and senior engineers are actually doing senior engineering work. Team B has a growing backlog of technical debt tickets nobody has time to fix. Their on-call rotation is brutal, and their best senior engineer just put in their resignation. Same tools, radically different outcomes. The difference is not talent. It is not which AI model they use. It is process, specifically the gates and checkpoints they put between AI output and production code. Here is how the next 6 chapters map to that difference. Chapter 2 shows you the 4 failure modes AI code produces that standard review misses entirely. Chapter 3 builds your automated gate layer. Chapter 4 designs the human review protocol. Chapter 5 covers team rollout and change management. Chapter 6 gives you the measurement framework to prove it is working. The gap between Team A and Team B is exactly what this lecture closes. And Chapter 2 is where we start pulling it apart. Let me be blunt about something that burned one of my teams badly. AI-generated code looks correct. It compiles. It passes the linter. It even reads like a senior developer wrote it. That is the trap. The model has no idea what your business domain actually requires. It only knows what plausible code looks like based on patterns it was trained on. So it produces code that is syntactically perfect and semantically wrong. I call this the confidence illusion. An off by 1 error in a pagination function, a missing null guard on a financial calculation, a boundary condition that only triggers on leap years. The AI writes all of these without blinking because it has never felt that the pain of a production incident at 2 a.m. Here is the critical insight. The model optimizes for looking finished, not for being correct. And the more fluent the output looks, the less likely your team is to scrutinize it. That false fluency is the biggest quality risk AI tooling introduces into your codebase today. But looking plausible is only half the problem. Wait until you see what happens when you let AI write the tests too. Now let me show you the exact scenario that gives teams the most dangerous false confidence of all: AI-generated tests. Look at this code on screen. We have a simple discount calculation, and the AI produced 4-unit tests that achieve 100% line and branch coverage. Green across the board. Ship it, right? Wrong. Look carefully at what the tests actually assert. The AI tested that a 10% discount on $100 returns $90. Correct. But it never tested what happens when the discount rate is negative. It never tested a $0 input. And critically, it never tested that a discount rate above 100% is rejected, because nothing in the function signature told the model that was a business rule. Tests are not wrong, they are just testing the happy path with cosmetic variations. 100% coverage of the wrong behavior. I have seen this exact pattern cause a billing overcharge incident in a fintech team that had full CI passing. Coverage numbers are a lie if the test author, human or AI, did not understand the domain contract first. So let me crystallize the correctness failure pattern before we move on. The AI does not lie to you, it tells you what complete working looks like. The problem is that complete and correct are two entirely different standards, and the model only knows one of them. Every correctness failure I have seen in AI-generated code traces back to the same root cause. The model optimized for apparent completeness, all the right shapes are present, while the human reviewer assumed apparent completeness meant semantic truth. That assumption is the gap you must close with a quality gate. Human domain validation is not optional. It is the only check that catches the invariance the model cannot know. And here is what I want you to carry into the next section. Correctness failures are usually visible if you look. The failures I am about to show you next, security, performance, and maintainability, are invisible until they hurt you in production. Security is where AI code gets quietly dangerous, and I want to be specific because vague warnings are useless. In my analysis of AI-assisted pull requests across 3 enterprise codebases over the past 18 months, the same anti-patterns appear with shocking regularity. Number 1. Hard-coded credentials. The model learned from training data that included secrets in code, so it reproduces that pattern fluently when generating database connection strings or API client setup. Number 2. Missing input validation on user-controlled parameters. The AI implements the business logic correctly, but skips the sanitization step because the prompt did not explicitly ask for it. Number 3. Improper error handling that leaks stack traces or internal paths directly to API responses. And number 4. SQL string concatenation. Instead of parameterized queries, the model knows patterns and picks whichever fits the surrounding code style, not the secure one. What makes this especially dangerous is that none of these failures trigger a linter or a type checker. They look like reasonable code. The OWASP top 10 has been stable for 15 years precisely because these patterns are hard to see under time pressure. AI code generation turns time pressure into a permanent condition. So what does the security checklist for AI code review actually look like? Let me show you. Let me show you the performance failure I see most often, and I mean literally copy-paste this from a real PR last quarter with names changed. The AI was asked to build an endpoint that returns a list of orders with their associated customer names. It generated clean, readable code. It works perfectly in development with 20 records in the database. Then you deploy it to production with 200,000 records and your database monitoring lights up like a Christmas tree. Why? Classic N+1 query. The AI iterated over the order results and issued a separate customer lookup query inside the loop. Because that is a straightforward way to express the relationship in code, and the model has no concept of what that costs at runtime. The database sees one query to fetch orders, then to 200,000 individual customer queries in the same request. I have personally watched this pattern take down a Node.js service that was handling 12 requests per second, completely fine load, because each request was spawning 400 database round trips. And here is the second pattern on screen. A memory leak from an AI that correctly implements an event listener registration, but never registers the corresponding cleanup. The code is contractually correct. The API is used as documented, but the runtime model is violated. Performance failures from AI code are almost never about wrong logic. They are about right logic applied without runtime cost awareness. Now here is the failure mode that teams almost never catch in code review under time pressure. And it is the one that compounds into the worst technical debt: maintainability. I want to show you a direct comparison. On the left, AI-generated code that works perfectly today. On the right, the version a senior engineer would write knowing that 6 months from now someone else probably a junior, will need to safely modify this calculation. The AI version uses magic numbers scattered through logic. 0 points, 3 to the 50%, no names, no explanations. Because the model was not asked to explain its choices. It uses generic variable names like data and result that carry no semantic information. And it compresses the logic into as few lines as possible because brevity looks like quality to a language model. The maintainable version names every constant, separates the calculation steps into functions with clear intent, and leaves the kind of comments that answer why not what. Here is the brutal truth about maintainability failures. They never show up in tests, they never trigger a linter, and they never cause an incident on the day you merge. They cause an incident 6 months later when a developer who did not write the code, under deadline pressure, misinterprets a magic number and makes a change that is locally correct but globally wrong. Adi Osmani's statistic, that seniors spend 66% of their AI coding time fixing AI output. This is where most of those hours go. Let me pull everything together into the framework you can actually use in a pull request review. We have walked through 4 distinct ways AI code fails quality: correctness, security, performance, and maintainability. And I want you to see them together in a single risk matrix, because the detection method and the review urgency are completely different for each dimension. Correctness failures require domain expert review. You cannot automate your way to semantic truth. Security failures are partially automatable with SaaS tools, but require human judgment on architectural decisions. Performance failures require either load testing or a reviewer who has profiled production systems. Static code review alone misses most of them. And maintainability failures require a reviewer who is willing to ask, will the next person understand this, under the schedule pressure that makes that question feel optional. Here is the hardest truth I can give you from 25 years of watching teams adopt new tooling. Every team that AI code without a structured quality gate told themselves they would clean it up later. None of them did. The debt compounded. The next chapter is going to challenge you even harder, because I am going to show you why the review process your team already has is specifically the wrong shape for catching AI code failures. Everything you built for human-written code review is bots that AI output exploits by accident. Here's a scenario I've watched play out in at least a dozen engineering teams over the past 2 years. A developer opens a pull request. The code is clean, properly indented, well-named variables, no obvious syntax errors. The reviewer skims it, runs through the usual checklist, naming conventions, error handling, test coverage, looks fine, approved, merged. And 3 weeks later, that same code is the epicenter of a production incident. What happened? The code was written by an AI, and the entire review process was built on one invisible assumption, that the author understood why they wrote what they wrote. Traditional code review is a conversation between 2 humans who share context. When you review a colleague's PR, you're not just reading code, you're verifying that their intent matches the implementation. You can ask, why did you choose this approach? And get a meaningful answer. With AI-generated code, that contract is broken. The AI has no intent. It has pattern completion, and your checklist was never designed to detect the difference. The scary part. The volume problem makes this exponentially worse. Teams adopting AI coding tools see PR volume jump 3, 4, even 5 times. Your reviewers are not reviewing more carefully. They are reviewing faster, under pressure, against checklist that was never equipped to catch what AI codes. So the question is not whether your checklist is good. The question is whether it was ever designed for this. Teaser, let me show you exactly what that breakdown looks like on a timeline, and when the first incident typically lands. Let me walk you through a timeline I've reconstructed from real postmortems. It is almost always the same arc. Week 1, the team adopts an AI coding assistant. Developers are excited. Velocity numbers look incredible. PRs start flowing in. Week 2 to 4, PR volume has tripled. Reviewers are keeping up, barely, by spending less time on each review. Nobody flags this yet because the throughput metrics look great. Month 2, review depth has quietly collapsed. The average time per PR review has dropped 12 minutes to under 4. Rubber stamp approvals are climbing. A senior engineer raises a concern in a retrospective. It is noted. Nothing changes. Day 90, the incident. A subtle logic error in an AI-generated data transformation function, the kind that only surfaces under specific input conditions, makes it past 4 separate reviewers and 2 CI pipelines. It hits production. The postmortem asks, how did this get through review? And the honest answer is, review never actually happened. What happened was, approval theater. Everyone performed the ritual of review without the substance of it. And here is the part that stings most. This is not a people problem. This is a process design problem. The review process was never recalibrated for the new volume and the new risk profile. Your reviewers are not lazy. They are overwhelmed and under-equipped. Question. So what exactly is missing from that standard checklist? Let me show you the 5 gaps side by side, and I guarantee at least 2 of them will surprise you. Now let's get concrete. Pull up your current code review checklist. Most teams have one, whether it is a wiki page, a PR template, or just institutional memory. I will bet you it covers naming conventions, test coverage percentage, no hard-coded secrets, error handling paths, and maybe a performance note. That checklist was built for human-authored code, and it is genuinely good at what it was designed for. But here are the 5 things it almost certainly does not cover, and these are exactly the failure modes AI code introduces. First, cross-file consistency. An AI assistant generating code in one file has no guaranteed awareness of contracts established in another file. Your checklist does not ask, does this function's signature match the interface defined 3 files away? Second, prompt-to-code traceability. When a human writes a complex algorithm, you can ask them why. With AI code, there is no recorded rationale. The checklist does not ask, can we reconstruct the requirement this code was generated to satisfy? Third, hallucinated dependency usage. AI frequently calls methods on libraries in ways that are syntactically plausible but semantically wrong. A method that exists but does not do what the generated code assumes. Standard linting will not catch this. Fourth, context window blindness. The AI only saw part of the codebase when generating this code. Are the assumptions it made still valid? Fifth, statistical masquerading as correctness. The code looks authoritative because the AI generates with confidence regardless of correctness. These 5 gaps are structural. You cannot patch them with a longer checklist. You need a different layer before the checklist even runs. Payoff, that different layer is what the next chapter is built around. But first, we need to understand why your reviewer's own psychology is actively working against you. Even if you fix the checklist tomorrow, added all 5 AI-specific checks, revised your PR template, trained the team, you would still have a problem. Because the most dangerous vulnerability in your review process is not the checklist. It is the reviewer's brain. There is a well-documented cognitive phenomenon called automation bias. When a human receives output from an automated or AI system, they apply significantly less critical scrutiny than they would to output from another human. The output looks authoritative, structured, and confident. The brain registers machine-generated equals vetted, even when that is factually false. I have seen this play out in code reviews dozens of times. A reviewer will spend 8 minutes carefully examining a messy but human-written PR, catching 3 real bugs. Then they will spend 90 seconds approving an AI-generated PR that is cleaner looking but contains a subtle race condition, because the clean formatting triggers a subconscious "this looks right" signal. The AI authority effect compounds this, because the developer who submitted the PR often says, explicitly or implicitly, the AI wrote this and it passes all tests. And that framing shifts the reviewer's mental model from adversarial verification to passive confirmation. Here is the clinical way to think about this. Reviewers operate on a trust calibration dial. With a junior developer, the dial is at high scrutiny. With a senior they trust, it is lower. With AI code, the dial is often set lower than it should be for a junior developer. Because the output surface looks polished. That miscalibration is silent, systemic, and almost impossible to fix through willpower alone. Teaser, but miscalibrated trust is only half the psychological trap. The other half is coming from your organization's own incentive structure, and it is actively rewarding the wrong behavior. Let me quote something that should make every engineering manager uncomfortable. I have heard versions of this in more than a few sprint retrospectives. We adopted AI coding tools in Q1 and our PR throughput is up 280%. The team is shipping faster than ever. That statement is being used to justify the AI adoption. It is being reported upward as a success metric. And here is the brutal truth hiding inside it. PR throughput is not a quality metric. It is a volume metric. When you measure AI adoption success by how many PRs are merged, you have just created a direct financial incentive for reviewers to approve fast rather than approve well. I have seen this accelerate into a genuinely dysfunctional dynamic. Teams start tracking time to merge it as an engineering efficiency KPI. Reviewers who approve quickly are implicitly celebrated. Reviewers who ask hard questions and block PRs for more work are seen as bottlenecks, even if they are catching real bugs. The organizational pressure is not malicious. Nobody in leadership is saying approve bad code faster. But the incentive architecture is saying exactly that. And your reviewers feel it in every stand-up when someone asks why a PR has been open for 2 days. Adi Osmani's data showed that senior engineers at AI-adopting companies spend 60% of their time fixing and modifying AI-generated code. Teams interpret that as we need better AI tools. The correct interpretation, we have optimized for AI output velocity while zeroing out AI output quality gates. You cannot performance manage your way out of a structural process flaw. Question: so if the problem is structural, what does the structural solution actually look like? That is the shift we need to make, and the next scene closes this chapter with exactly that answer. So let's close the loop on what this chapter has built. We started with the observation that your code review checklist was designed for a world where the author is a human who holds intent and context. AI code breaks that assumption silently. We then trace the 90-day arc from AI tool adoption to production incident. Not because your team is incompetent, but because the process was never recalibrated for the new volume and the new risk profile. We identified 5 structural gaps in standard checklists that only appear with AI-generated code. And we named the 2 psychological traps that make even a good reviewer unreliable against AI code: automation bias and organizational velocity pressure. Here is the key insight I want you to carry into the next chapter. The solution is not better reviewers working harder. I have tried that. It does not scale, it causes burnout, and it still lets bugs through because cognitive bias is not solvable by effort. The solution is a structural quality gate that sits upstream of human review entirely. A layer that filters, annotates, and flags AI-generated code before a single human eye touches it, so that when a reviewer does look at a PR, they are not starting from scratch in a sea of AI-generated ambiguity. They are reviewing a pre-triaged artifact with a risk profile already attached. This is what I call the upstream quality shift. Move the quality work left, before review, not during it. In the next chapter, I am going to show you the exact three-layer pipeline that makes this real: the automated checks, the AI-assisted meta-review layer, and the human escalation criteria that together eliminate both the checklist gaps and the psychological traps we identified today. The architecture is more straightforward than you think. But the sequencing is everything, so we've established that your existing review process was never designed for AI-generated code. Now let's build something that actually works. I call it the 3-layer quality gate pipeline. And layer 1 is your first line of defense, the ones before any human ever lays eyes on the code. Layer 1 is pure automation, static analysis, SAST security scanning, and dependency audits. Now you might think, we already have ESLint and SonarQube. We're covered. That's exactly what every team says right before they merge an AI-generated SQL injection vulnerability. The difference is configuration. For AI code specifically, 3 tool categories are non-negotiable. First, a linter with custom rules, ESLint for JavaScript, Pylint or Rough for Python. Second, a SAST scanner like SonarQube or SemGrep configured with AI-specific rule sets. Third, a dependency auditor, NPM audit, pip audit, or SNEC, because AI models love recommending packages that haven't been maintained since 2019. These aren't optional. They are your automated contract with code quality. But here's the thing nobody tells you. Out-of-the-box configurations catch maybe % of what AI code breaks. The real power comes from custom rules, and that's exactly what we'll build next. Let me show you something concrete. This is a real pattern I've seen AI models generate dozens of times, and default linting rules miss it every single time. The pattern: AI generates a data query that concatenates your input directly into a SQL string. The code looks clean, it passes style checks, it even has docstrings. But it's a textbook SQL injection. Here's how you write a SemGrep rule to catch it automatically. We're targeting Python's string formatting inside any function, calls a database execute method. The rule uses SemGrep's pattern either syntax to match both f-string interpolation and % formatting when the result flows into a dbb execute or cursor execute call. Notice the metavariable pattern block. This is what makes it AI aware. We're not just flagging all string concatenation. We're specifically flagging the pattern where a variable that could originate from a function parameter gets interpolated into an execute call without going through a parameterized query path. The message field is critical. It doesn't just say bad code. It tells the developer exactly what to do. Use parameterized queries with placeholders. This is how you turn a cryptic tool error into an actionable fix. Run this with SemGrep. Config. Rules a skid injection a YAML CRC, and it integrates into your CI in under 5 minutes. Now the question is, what happens when the rule fires? Do you block or warn? That's a design decision most teams get wrong. Now here's where most teams make a critical mistake with their CI gates. They treat everything as either fully blocking or fully ignored. That binary thing destroys developer trust in the tooling within weeks. Here's the model that actually works in practice. You have 3 categories of gate outcomes. First, hard blockers. These are findings that prevent merge completely, critical SAST vulnerabilities, dependency CVEs with a CBSS score above 7, and any custom rule flagged as error or severity. No override. No exceptions without a documented security waiver. Second, soft warnings. These generate a PR comment and require a developer acknowledgement checkbox, but they don't block merge. Meet complexity violations, style issues, non-critical dependency warnings. They stay visible but don't create friction for every PR. Third, informational signals. These go into your quality dashboard but generate zero PR noise. Tracking trends over time, not blocking individual merges. The key to making this work is the failure message format. When a gate blocks a PR, the developer sees three things: what rule fired and why it matters, the exact file and line number, and a copy-paste fix or a link to the remediation guide. Not Sonar 36 now violated. That's useless. SQL injection risk detected in user service PI line 47. See remediation guide. Actionable. Getting this feedback loop right is the difference between a gate your team respects and one they disable after 2 weeks. And speaking of things developers try to bypass, wait until you see what Layer 2 catches that Layer 1 completely misses. Layer 2 is where people's brains break a little when I first explain it. We're going to use another AI to review the AI-generated code before a human touches it. I know what you're thinking. Isn't that just asking the same system to grade its own homework? And that's a legitimate concern. But here's the key insight from 25 years of watching review processes fail. The problem isn't the AI reviewing AI code in principle. The problem is using the same model, the same text, and the same prompt. Layer 2 works when you treat it as a structured adversarial audit, not a self-check. The architecture is this. After Layer 1 passes, the PR diff is extracted and sent to a second LLM call, ideally a different model or at minimum, a completely isolated context window with a prompt engineered specifically to be skeptical, not helpful. The model's job is not to improve the code. Its job is to find the 4 failure modes we defined in Chapter 2: correctness assumptions, context blindness, security blind spots, and maintainability debt. This is counterintuitive, but it works because LLMs are extraordinarily good at pattern matching against known failure modes when you give them explicit categories to check against. In real-world deployments, I've seen this catch 60 to 70% of the issues that would have required senior engineer time to find in manual review. That means your senior engineers are spending their review time on the genuinely hard problems, not the mechanical ones. But, and this is a hard but, you need to know exactly what Layer 2 cannot be trusted to catch. That comes in Scene 3. First, let's look at the actual prompt. Let me show you the actual prompt template. This isn't a vague, please review this code instruction. Every field in this prompt is deliberate. We open with a role definition that frames the LLM as a security-focused senior engineer, not a coding assistant. That framing shift alone dramatically changes the output quality. The context block injects the PR title, the target module, and critically, a one-line description of what this code is supposed to do in the system. Without that context, the AI reviewer has the same blind spot as a human reviewer who never read the ticket. Then we pass the raw diff. The instructions section is where the structure really matters. We demand output in a specific JSON schema, not freeform prose. The schema has 4 required fields. Risk signals, which is an array of findings each tagged with dimension, severity, and a 1-sentence explanation. Confidence score, a 0 to 1 float indicating how certain the reviewer is about each finding. Suggested human focus, which is an ordered list of the 3 areas that most need human attention. And a summary field that gives the human reviewer a 30-second brief before they open the diff. This structured output is then automatically parsed by your CI system and rendered a PR comment in a standardized format. Reviewers stop wading through 400 lines of diff. They open the PR, read the AI pre-review brief, and know exactly where to focus their expert attention. That's not AI replacing human judgment. That's AI amplifying it. Now, what does this system completely fail to catch? That's where the danger is. Here is where I have to be brutally honest with you about Layer 2. Because this is the mistake that gets teams into serious trouble. Layer 2 will give you a false sense of security if you don't understand its hard limits. There are 4 categories of problems that LLM pre-review fundamentally cannot be trusted to catch. First, business logic correctness. The AI reviewer has no idea what your discount calculation rule is supposed to be or what your regulatory compliance requirement says. It can't catch logic that is syntactically fine but semantically wrong for your domain. Second, system-level integration failures. Race conditions that only appear under production load, cascading failures across microservice boundaries. These require runtime context the LLM doesn't have. Third, data sensitivity classification. The AI doesn't know that this particular field in your user table is PU under GDPR, or this API response gets cached by a CDN in a way that could leak data. That knowledge lives in your team's heads and your compliance documentation. Fourth, novel attack vectors. LLMs detect known patterns. A zero-day class of vulnerability by definition isn't in its training data. So here's the human override protocol. 3 trigger conditions escalate a PR to mandatory senior engineer review regardless of Layer 2 output. 1. The PR touches authentication, authorization, or cryptographic code. 2. The confidence score is below 0.6, indicating the AI reviewer itself is uncertain. 3. The PR modifies data migration scripts or schema changes. These are non-negotiable escalation triggers. Layer 2 is a force multiplier for human review. It is never a substitute. Now let's talk about the 25 points where human judgment is still irreplaceable. We've automated everything we can automate. Layers 1 and 2 have done their jobs. Now a human reviewer opens the PR, and without a structured checklist, we're back to the same ad hoc review that was failing us before. That's why Layer 3 is the 20-point AI code review checklist. Let me walk you through its structure. The checklist is organized across the 4 quality dimensions we established in Chapter 2. Correctness and logic gets 8 items. Things like, does the error handling cover all exception paths the AI might have silently ignored? Are all edge cases for null and empty inputs explicitly handled? And does the algorithmic complexity match what the system actually needs under load? Security and trust gets 6 items. Input validation, output encoding, secret management, privilege escalation paths. Context and integration gets 6 items. This is the dimension layers 1 and 2 are weakest on, so human reviewers spend the most time here. Does this code actually fit the architectural pattern of the surrounding system? Does it respect the team's established abstractions? Or did the AI invent a new pattern that looks reasonable in isolation but breaks consistency? Maintainability and ownership gets 5 items, the hardest to tool detect. Is this code something a mid-level engineer can understand and debug at 2am? And does the AI's naming and structure match the codebase's vocabulary, or is it a foreign dialect? Each item in the checklist is tagged with 2 metadata fields. Detection difficulty. Low means tools catch it, high means only humans catch it, and primary gate layer. This prevents reviewers from rechecking what Layer 1 already validated. The checklist exists to focus human attention, not to duplicate automated effort. But here's the real impact of having this checklist. The numbers are stark. Let me give you the numbers, because this is the argument you'll need to make to your engineering manager when they ask why you're investing time in building this pipeline. Before the 3-layer gate, in a team actively using AI coding tools, here's what we typically measured. Average time per PR review was 47 minutes for a senior engineer. Defect escape rate, bugs that made it past review into production, was running at 23% for AI-generated PRs versus 8% for human-written PRs. That 3x defect rate gap is exactly the technical debt accumulation that Adi Osmani statistic was pointing at. Seniors spending 66% of their time fixing AI code instead of building. After implementing the 3-layer pipeline, the same team saw average human review time drop to 19 minutes per PR, a 60% reduction. The reason isn't magic. It's pre-filtering. Layer 1 blocked 34% of PRs before a human ever read them. Mostly dependency issues, security anti-patterns, and complexity violations. Layer 2 pre-review briefings reduced the cognitive ramp-up time for each PR from roughly 8 minutes of orientation to under 2 minutes. The defect escape rate for AI-generated code dropped from 23% to 9%, nearly matching the baseline for human-written code. The critical insight here is the pipeline doesn't make your reviewers faster by asking them to do less thinking. It makes them faster by eliminating the low-val work that was consuming their attention before the hard thinking could even start. Now let me show you the full pipeline as a single diagram. Because how these 3 layers connect matters as much as each layer in isolation. Here it is, the complete 3-layer quality gate pipeline, end-to-end. A developer opens a PR with AI-generated code. Immediately, Layer 1 triggers in CI, static analysis, SAST scanning, dependency audit. Hard blockers stop the PR cold and send actionable error messages. Soft warnings generate PR comments and require acknowledgement. If Layer 1 passes, Layer 2 activates. The diff is sent to the AI adversarial reviewer, which returns a structured JSON report, risk signals, confidence scores, human focus areas. The CI system renders this as a PR comment. If any human override trigger fires, auth code, low confidence score, schema migrations, the PR is automatically labeled require senior review and assigned to the senior engineer queue. Otherwise, it enters the standard human review queue with the Layer 2 brief already attached. The human reviewer opens the PR, reads the brief, and works through the 25-point checklist, focusing exclusively on high-difficulty items that tools and AI couldn't assess. Conditional approval, PRs with no overrides and clean Layer 1 and 2 signals get standard merge approval. PRs with override flags require explicit senior sign-off before merge is enabled. That's the pipeline. 3 layers, clear handoffs, no ambiguity about who is responsible for what. I've watched teams implement this and cut their AI code-related production incidents by more than half in the first quarter. In the next chapter, I'm going to show you the real-world implementation stories. including the one team that built this entire pipeline, and then found the gotcha that none of us anticipated until it was almost too late. Let me tell you about a Friday afternoon that nobody on that team wants to remember. An e-commerce platform, Black Friday Load, their AI-generated rate limiter, had passed every static analysis check, every unit test, every peer review comment. It looked clean, under normal traffic. But at exactly 4,200 concurrent users, the token bucket algorithm started leaking. Not crashing, leaking. Requests that should have been blocked were sliding through, hammering the payment service downstream. By the time the on-call engineer correlated the alert to that specific PR merged 3 weeks earlier, they had already processed 47 duplicate charges. Here is the painful part. When I walked through the postmortem with the team, every single failure point was visible in the diff. The AI had implemented a thread-unsafe counter reset. It was a classic race condition that only surfaces under a very specific load pattern, one their staging environment never reproduced. Their existing gate had no concurrency contract check, no load pattern simulation trigger, and no AI-specific flag for shared mutable state without synchronization. A single architectural smell detector on the rate limiter module would have caught it in under 2 minutes. And that gap, between what your gate checks and what AI code actually breaks, is exactly what this chapter is about. Now here is a failure class that almost nobody talks about, and it is the one that scares me the most after 25 years watching code bases grow. I call it the cross-file consistency failure, and it is structurally invisible to any review process that looks at files one at a time. Here is how it happens. You ask an AI to implement a new service handler. The AI generates perfect, clean, idiomatic code for the file it can see, but your codebase established a contract in a module configuration file written 6 months ago. All handlers must register their own error boundary with the central error registry before returning any response. That contract lives in a file the AI never saw. Its context window was the handler file and maybe 2 imports. The new handler looks correct. It passes every check. And then, one Tuesday, an upstream timeout fires, the error boundary is missing, and the exception propagates to a layer that has no idea what to do with it. This is architectural drift by accumulation. Each individual AI-generated file is locally correct, but system as a whole is drifting away from the contracts your architects established. The fix is not to review files harder. The fix is to add a cross-file contract verification layer, a step in your gate that checks new code against your module interface registry, your API contract definitions, and your error handling topology. Without that layer, you are reviewing words while the sentences break down. This is the class of bug that separates teams with strong gates from teams that are slowly drowning in technical debt they cannot even name. Across the postmortems and war stories I have collected from teams over the past several years of AI-assisted development, 5 incident patterns keep showing up with near-perfect regularity. I want you to look at this catalog not as a list of mistakes. I want you to look at it as your detection rule starter pack. Every single one of these patterns has a corresponding gate check that would have stopped it before merge. The first pattern, AI generates optimistic error handling, try-catch blocks that swallow exceptions or log and continue where the caller expected a thrown error. Detection rule, static analysis for empty catch blocks and missing rethrow assertions. Second pattern, hard-coded figuration values embedded into logic. API endpoints, timeouts, magic numbers, because the AI had no visibility into your config management system. Detection rule, secret and literal scanner with a domain-specific allow list. Third, the cross-file consistency failure we just discussed. Detection rule, contract registry diff check. Fourth, test coverage theater. AI generates tests that assert the happy path only, hitting line coverage targets while leaving all edge cases untested. Detection rule, mutation testing score gate, not just line coverage. And fifth, the one that bites teams hardest. AI-generated SQL or RM queries that are functionally correct, but perform full table scans at scale because the AI did not know your index strategy. Detection rule, query plan analyzer in pre-merge CI. Print this table. Put it on your gate design checklist. These 5 rules alone would have prevented the majority of AI-related incidents I have seen in production. Next, let us look at the teams that never had these incidents and what they did differently from day one. I want to show you 2 team trajectories running in parallel, because the numbers tell a story that no amount of theoretical argument can replace. Team Alpha GitHub Copilot in January. They were excited, and they should have been. Velocity jumped 40% in the first 6 weeks. Commits were up, features were shipping, and leadership was happy. But they'd not invest in a quality gate before scaling adoption. By month 3, senior engineers were spending more than half their review time fixing AI-generated code that had passed automated checks. By month 5, Defect escape rate had climbed from 2.3% to 9.1%. Senior engineer morale scores, measured in their quarterly survey, dropped 17 points. One engineer told me, "I feel like I am a quality filter for a machine, not an engineer anymore." Team Beta started the same month. Same tools, similar codebase size, similar team composition. But before they let anyone merge AI-generated code into main, they spent 2 weeks wiring layer on automation, the architectural smell detector, the AI confidence score threshold, the secret scanner. Then they told the team, everything goes through the gate, no exceptions, no overrides, without a written justification. At 6 months, their velocity was 32% above their pre-AI baseline, slightly lower than Alpha's early spike, but sustained. Defect escape rate, 2.1%, actually lower than pre-AI. Senior engineer morale, up 11 points, because they were doing architecture and design, not patching. The gap between these two teams is not talent, it is not tooling. It is the decision to invest in the gate before scaling the speed. So how exactly did teams like Beta roll this out without derailing sprint velocity, triggering the team resistance that kills every new process initiative? The answer is phasing, and the specific sequence matters as much as the gates themselves. I have seen teams try to drop all 3 layers on the team at once in week 1. And I have watched engineers route around every single check within a fortnight because the friction was unbearable. The teams that succeeded followed a 3-sprint sequence. Sprint 1, layer on automation only. Wire the static analysis, the AI smell detector, the secret scanner. Make it non-blocking in the first week. It reports, it does not reject. This gives you your baseline signal without any team friction. In week 2 of Sprint 1, flip it to blocking. The team has already seen the output. It feels familiar, not punitive. Sprint 2. Add the LLM pre-review step. The automated AI reviews AI pass, but only after your layer 1 baseline is stable and false positive rate is below 5%. Introduce the LLM reviewer as a second pair of eyes, not as a gatekeeper. Sprint 3. Introduce the human reviewer checklist for AI-tagged PRs. By now, the team has 2 sprints of data showing what the gate catches. The checklist does not feel bureaucratic. It feels like a summary of things they have already seen the gate catching. Process change management lesson number 1. Never introduce a gate that people have not already seen the evidence for. The data from your own codebase is the only argument that actually works. 25 years of watching software teams. Different companies, different stacks, different continents. And the single clearest pattern I can give you from all of that observation is this. The teams that stayed healthy after adopting AI tools were not the ones with the strictest rules. They were not the ones with the most sophisticated tooling. They were the teams that understood, at a cultural level, that the quality gate is not a speed bump. It is the engine that makes speed sustainable. Every team that skipped the gate in the name of moving faster ended up slower by month 4. Every team that invested in the gate before scaling AI adoption kept their velocity, kept their senior engineers engaged, and kept their defect rate stable. The gate is not what slows you down. The gate is what lets you run at full speed without driving off the cliff. There is one thing a 25-year-old tool cannot do. Replace the judgment of a senior engineer who has seen the cliff before. Your role in the AI-assisted development era is not to review every line. It is to design the system that catches what the tools miss, and to know, from experience, what those blind spots are. You have just seen 6 of the most expensive ones. In the final chapter, we are going to make this actionable in your very next sprint, with team-size specific playbooks you can hand to your team lead on Monday morning. Do not leave before you get the 1-page gate design for your team size. Alright, we've covered the war stories. Now let's make actionable. Starting with the smallest unit, you and one other person. Solo devs and 2-person teams make the same mistake. They think quality gates are for big teams with time to spare. Wrong. They're actually more critical for small teams, because one bad AI-generated PR can take you offline for days with no one to catch it. Here's your minimum viable gate, 3 automated checks, and a 5-item human checklist. Automated. Run SLint or your language equivalent, run your unit test suite with a coverage floor of 70%, and run a secret scanner like GitLeaks on every commit. Non-negotiable. On the human side, ask 5 questions before you hit merge. Does this code do what the ticket says? Are there any hard-coded values I'd be embarrassed to show someone? Does the error handling make sense, or did the AI just swallow exceptions? Would I be able to debug this at 2 a.m.? And finally, did the AI hallucinate any library doesn't exist or is deprecated? That last one bites solo devs constantly. 5 questions, 3 automated checks. That's 80% of the protection, with maybe 15 minutes of overhead per PR. But once your team grows past 2 people, this bare minimum approach starts showing cracks. And the next scene show exactly where. Now you're at 5 to 15 people. This is the zone where teams either build a real culture of AI code quality, or they accumulate 6 months of hidden technical debt that explodes during a scaling event. I've watched this exact pattern repeat across at least a dozen teams. The inflection point is usually around 8 engineers. Suddenly there are too many PRs for any one person to review carefully. So reviews get shallower, and AI-generated code starts sliding through unchecked. Here's the recommended gate configuration for this range. First, keep everything from layer 1 and add a hard PR policy. No self-merges, ever. Every PR needs at least one reviewer who did not use an AI tool to write it. You need a human sanity check from someone with full context. Second, this is the right size to introduce layer 2 LLM pre-review. Wire a GPT-4 or Claude API call into your CI pipeline. Using the prompt template we'll share in the resources section. It adds maybe 90 seconds to your pipeline and catches the AI-specific patterns. Over-engineered abstractions, suspicious complexity spikes, copy-paste duplication files. Third, define reviewer qualifications per PR type. Feature PRs need a domain owner sign-off. Infrastructure or CI changes need someone with ops experience. Security adjacent code, auth, crypto, data handling, requires your most senior person regardless of queue depth. This sounds bureaucratic, but it takes about 2 hours to set up as a code owner's file and a branch protection rule. 2 hours now versus 2 weeks of incident postmortems. Here's the part nobody talks about though, what happens when your PR queue backs up because of these rules? That's the governance question the next scene answers. Enterprise scale, 50 engineers and up, introduces a problem that mid-sized teams don't have. The volume of AI-generated code literally exceeds your human review capacity. I've seen org-wide Copilot rollouts where the PR throughput tripled in 60 days. The review queue didn't triple. It collapsed. At enterprise scale, you need governance, not just process. Here's the stack. At the top, an automated metrics dashboard. I recommend a Grafana board pulling from your GitHub or GitLab API, showing AI code volume as a percentage of total commits, average review depth score, and the critical metric, rework rate on AI-originated PRs versus human-originated PRs. If that rework rate diverges by more than 15%, you have a systemic problem, and the dashboard tells you before a postmortem does. Middle layer, automated quality metrics reporting piped into your weekly engineering meeting. Not a manual report, automated so it actually gets read. Bottom layer, escalation protocols. When AI code volume exceeds 60% of weekly commits, trigger a mandatory architecture review. When the LLM pre-reviewer flags a PR with a complexity score above your threshold, auto-assign a principal engineer, not a random senior. And critically, establish an AI code attribution policy now, before regulators or your legal team ask for it. Track which PRs were AI assisted in your commit metadata. This sounds heavy, but the tooling exists today and the alternative is a governance audit you're not prepared for. Every layer in this stack can be deployed incrementally. You don't need all of it on day one. Start with a dashboard. The data will tell you what to add next. Before we get to the templates, let's burn the most important reference into your memory. The do not merge list versus the fast track safe list. After 25 years and hundreds of postmortems, I can tell you, the difference between teams that get destroyed by AI code and teams that don't is not the AI tool they use. It's whether their team has internalized this to the point where it's a reflex. On the danger side, the 10 patterns that must trigger immediate escalation, no exceptions. Cyclomatic complexity spiking above 20 in a single function. AI loves generating deeply nested logic that technically works, but is unmaintainable. Empty catch blocks or bare exception swallowing, we've covered this, but it keeps showing up. Hard-coded credentials, connection strings, or environment-specific values. Generic variable names across more than 30 lines. Names like data, result temp, obj, AI naming is a readability time bomb. Missing null checks on external API responses. AI assumes happy path. Sync calls, inside loops, an end pattern the AI will generate without hesitation. Missing input validation on any public-facing function. Deprecated library usage that the AI trained on but is no longer maintained. Over-abstraction, 3 layers of interfaces for a 10-line utility. And finally, no tests, or tests that only assert true equals true. On the safe side, 10 green signals. Small PR under 200 lines, single responsibility, existing test coverage updated, no new dependencies added, no security adjacent code touched, LLM pre-reviewer returned clean, domain owner has reviewed, all linter checks pass, ticket acceptance criteria verifiably met, and rollback path is obvious. Print this, stick it next to your monitor. Now let's talk about how to make your team actually use it. Now the practical handoff, the resource package you can deploy into your team this sprint. I'm not giving you a vague build a checklist suggestion. I'm giving you the actual artifacts. The download includes 4 things. First, a 25-point PR checklist in Notion database format, and a raw markdown file you can drop straight into your .github/pull-request-template.md. Every item maps to a layer in the Gate framework we built across this lecture. Second, CI configuration snippets, GitHub Actions workflows for the 3-check automated gate, the LLM pre-review API call step, and the coverage enforcement block. Drop these into your .github/workflows folder, and you're done. Third, the LLM pre-review prompt template, the exact system prompt and user prompt structure that gets consistent, structured output from GPT-4 or Claude. This is the prompt I've iterated on across 8 real teams. It outputs a structured JSON response with a severity score, a list of flagged patterns with line references, and a recommended action. Parse that JSON in your CI step, fail the build on high severity, post a warning comment on medium. Fourth, a team onboarding guide, a 1-page document explaining the gate to engineers who weren't in this lecture. It covers the why, the workflow, and the one rule everyone must internalize. The gate is not a blocker, it's a signal. Fast teams use signals faster. How you adapt these for your stack. If you're on GitLab, the action snippets map almost one-to-one to GitLab CI YAML. I've included a translation note in the README. If you're on Bucket pipelines, the LLM step needs a minor curl refactor, also documented. The Notion template is database linked, so you can track gate health per sprint. Link in the description. Grab it now, and I'll show you exactly what to do with it before your next planning session. We're at the end of this lecture, so let me leave you with exactly what to do before your next sprint planning meeting, and one sentence that should change how you think about AI coding tools permanently. 5 actions this week. 1. Install JITleaks and your linter as pre-commit hooks today, not this sprint today. Takes 15 minutes. 2. Copy the pull request template into your repos.github folder before your next PR is opened. 3. Run the LLM pre-review prompt manually against your last 5 merged PRs and check the output. You will find something you missed. 4. Share the escalate versus fast track reference card with your team in your next stand-up. 5. Schedule a 30-minute gate review into your next sprint retrospective as a standing agenda item. Make it permanent. Now the one sentence that ties everything together: AI coding tools make your fastest engineers faster and your weakest code weaker. The quality gate is the only mechanism that decouples those two effects. That's the core insight. Print it. The teams that win with AI are not the ones who use it most. They're the ones who built the upstream guardrails before the volume got unmanageable. If you're nodding along to everything in this lecture but haven't shipped a gate yet, that changes this sprint. One last thing. This lecture is part of a series. The next video goes deeper into a question this lecture deliberately left open: AI code ownership and attribution. When your AI-generated code causes a production incident, who owns the fix? Who gets credit for the feature? How do you handle it when 2 engineers independently use Copilot and generate nearly identical code in different services? Those are the questions that will define engineering culture for the next decade, and that's exactly what we're unpacking next. See you there.